Welcome to our presentation on Robot Sensor Interface, also known as RSI and Force Torque Control. My name is Pat Duda. I'll be giving you an overview of what these technologies are and what they can do. RSI is an interface that gives the ability to incorporate real-time sensor feedback into your robotic application. Any sensors that can be connected to the I/O system can be used, and it also has interfaces that enable remote control of the robot by other systems or devices. This opens the possibility to program with what I would call behaviors, in addition to program points. RSI is a mature and robust interface that has been around since 2002. It's implemented as a hard real-time performance system, which means that it's guaranteed to perform all the calculations and adjustments on every sensor cycle of 4 milliseconds. It's available on all robots and controllers with our KUKA system software. Note that it's not available on Sunrise and iKUKA software, which have different features that have similar capabilities. So for example, if you wanted the robot to follow a surface, you normally would program a path with many points to follow the surface. But with RSI, you could set up a distance sensor behavior to follow the surface at a certain distance away. Then you could program a single point for the start and end of your path, and the RSI behavior would handle detecting the surface and automatically adjust the path to maintain a certain distance from the part, regardless of the shape of the surface. Force Torque is another tech package which is built on top of RSI. It enables use of 6-degree of freedom force sensor input on the robot end effector. It supports any sensor that can get input into our field bus systems. ATI sensors are best in class, and we have extended driver capability for them. The system handles advanced math for calculating force at any working TCP point, regardless where the sensor is mounted. It has friendly wizards to set up applications of different types, like search for contact, track during contact, and adjust grinding speed. The wizards actually generate RSI programs for you. However, you can also use the Force Torque RSI blocks to create custom control applications, so the sky's the limit on what you can achieve. So what can you do with these packages? One key capability is that the robot can react to tolerances in the work pieces or the environment that normally you wouldn't be able to program for. For example, following a weld seam where a part may warp or have variances. Another example might be assembling parts that have tolerances tighter than the robot positioning capability. The external interfaces support connection with remote systems that could remote control the robot or do a data collection and analysis. This also supports connection to systems that might have very advanced control algorithms that could do things beyond the capability of a normal robot controller. A better way to explain some of the capabilities is to look at some videos of real-world applications. This is a demonstration of how force torque control can be used to assemble the components of a planetary gear. Planetary gears are difficult to assemble because of the multiple floating gear pieces that all must be meshed into a single base gear. The process begins by doing a search to determine when the gear makes contact with the base. Then it begins an insert process that uses multiple RSI and force torque behaviors together. One behavior is generating a downward force, and another is applying a wobble motion in multiple axes. This is all overlaid on a simple programmed motion to insert the gear. These sort of behaviors work together to generate a human-like capability that can get the independent gear pieces to align and mesh properly. The process also implements a sensing behavior to feel when the gear drops into place, so the robot knows the task is complete. You'll notice in the upper left corner the RSI monitor graph, which is showing a live feed of the process forces. This provides excellent feedback for debugging and process monitoring. It's a very valuable tool that helps to correlate between visual observations and the control behavior of the robot. This example shows a standard seam tracking product from Servo Robot that is used in welding. This system uses a laser line camera that determines the position of the weld seam. The remote camera system uses the RSI open interface to tell the robot whether to offset right or left to stay in the seam. This enables the robot to achieve good process welds regardless of whether the part is properly positioned or warped. This is an example of an advanced grinding system from Nidec Minster. It uses force torque and RSI together to create advanced user-friendly capabilities for large casting grinding. They implemented a wireless remote control to safely move and guide the robot from outside the system guarding. You can see the operator in the lower left controlling the motion. The game-style controller is familiar to many people. It provides joysticks to do fine control and function buttons to activate different features. This enables an operator to control a very large grinding and cutting wheel very easily from a safe place. It utilized the standard force torque feature to manage cutting feed speed to stay within process limits. It also enables the operator to control feed speed with haptic feedback to warn when he is exceeding proper limits. The system can be set up to follow a surface to ensure quality. It even gives the capability to do remote teleoperation with a camera. So how is it possible to do all this? RSI programs are activated as a parallel real-time task that runs alongside the main KRL program. Normal motion planning happens in KRL. RSI adjustments are added to the normal motion plan every 4 milliseconds. One of the main differences between RSI and some competitor offerings is that RSI is a hard real-time system. Some other systems can do a process as a background program, but it behaves the same as if you used our background SPS. That is, the processing time can change depending on factors like what calculations are in that program or other processing loads on the controller. This can have a huge impact on the behavior and reliability of a sensor feedback application. That's the difference. RSI's hard real-time design is guaranteed to process and update the sensor control loop every 4 milliseconds. The programming is quite simple. There's a command to load the RSI program. Then the RSI on call activates the RSI program in the background. The program can continue to do normal motion commands in KRL, and there's no special programming otherwise. When the sensor feedback is no longer needed, it's turned off with a single command called RSI off. So that's how it's added to your KRL program. The other piece is creating the RSI program. RSI is a block-based programming environment. It has a graphical editor that is added to work visual when you add the option package. The programs are visible in the left file panel. The right panel shows the toolbox of different blocks that are included with the system. It even has the capability for you to create your own blocks and toolboxes containing behaviors you would want to reuse. The center panel shows how an RSI program looks. Blocks can be inserted and wired together with drag and drop. Some of you might be familiar with other software that has a similar block programming paradigm. like LabVIEW by National Instruments or Simulink by MATLAB. Blocks in RSI can have signal inputs, data that flows into the block on the left, and signal outputs, data that flows out as a result of the block processing on the right. Blocks can also have parameters inside that define how it processes or behaves. This example shows a triangle signal generator block. It has the ability to take parameters like amplitude, frequency, phase, and offset. On this block, some of these can also be passed as inputs. This is the help page for the triangle block. You can see the block help file gives a detailed description of the inputs, outputs, parameters, and behavior of the block. RSI comes with an extensive library of blocks. Communication blocks provide means to get different sensor data in and out of RSI. The basic rule is that anything you can get on the KUKA field bus, you can use in RSI. In addition to the normal field bus I/O, RSI includes an Ethernet communication block, which enables UDP communication with another computer. The data exchange is formatted in a readable XML format. This enables connection to systems that offer data logging, remote control, or advanced control algorithms. There are motion manipulation blocks for controlling axis-based or Cartesian XYZ-based adjustments. The override speed of the program execution can also be controlled. Important robot data is available to RSI, like robot and axis positions, motor currents, and gear torques. Position data is available for a future window of the motion plan and actual measured feedback from the last 4 millisecond cycle. And lots of math functions are available to calculate adjustments. Logic blocks can also be included in the signal flow calculations. Finally, many control systems blocks are included. They range from a simple proportional gain to a PID control to a generalized 8th order transfer function. Powerful filtering blocks are also available for smoothing data. Let me show you what the experience is like when you create an RSI program. At the beginning, we used the simple example of a height regulation application with a laser sensor. This is the process to build that program. This recording is slightly accelerated, but the total programming time for this is about 5 minutes. We drag and drop blocks from the palette on the right to the center editor window. We begin by adding an analog input block for our sensor data. We also need a set point height, so we add a SendPria block, which lets us read real floating point values from KRL. A proportional gain will scale the analog value to millimeters. So we have our sensor value and our set point, and we need to calculate the error difference between them with the subtract block. So we just drag that in, and we can connect the wires. Next, we'll add a pose core block, which stands for position correction. This makes the adjustments to the normal planned motion. We can select a drop-down at the bottom to define if the adjustments are in base, tool, or several other coordinates. So we wired our adjustment into the Z. So the adjustments will be in Z of base. Initially, we might think it's good to put the error adjustment directly into the position correction, but keep in mind that the system will try to do this adjustment in 4 milliseconds. Since it's a closed-loop feedback system, we can add a proportional gain to make the adjustment small for each 4 millisecond cycle. We can also add a limit block, which will essentially limit the adjustment to a certain velocity that's within the capability of the robot. We must add a pose core safety monitoring block that limits the total amount of correction that the pose core block can do. So this is our basic program. We can move and arrange the blocks easily with selection, drag, and drop. Finally, we add a monitor block that connects into the RSI signal graph for debugging. We can drag or connect any signals we think are useful. When the program is done, we can use the online editing tools to transfer it over the network to the robot. The monitor block will automatically connect to the RSI monitor signal graph if it's displayed on the SmartPad. The graph can be a valuable debugging and monitoring tool. It has the capability to record and store the graph in a text file that can be read and analyzed in other software. The monitor block also has the capability to send the data to a remote computer on the network, but it requires custom software to receive the data. Now let's switch over and talk about force torque control for a few minutes. As mentioned before, force torque has helpful step-by-step wizards to configure an application. It also has template programs and inline forms to add the proper program statements into your KRL program. The main application types are divided into sensor-guided and superimposed. Sensor-guided types don't require any programmed path. They are completely guided by the sensor input. Superimposed types overlay the force control behavior onto a programmed path. Each one has a make contact profile to search for contact with a part and a tracking during contact to enable more control flexibility after initial contact. The velocity adaptation option has the capability to adjust feed speed for grinding and cutting applications that need to follow a defined path. The force torque package also comes with a load data calibration program to determine the mass and CG for the tool attached to the force sensor. This is not to be confused with the load data determination tech package that determines the mass, CG, and moment of inertia for the entire end-of-arm tool. The force control can work in many different coordinate systems. Tool and base are commonly used. Tool is good for manipulating parts for things like assembly work. Base is good for applying force against a fixed working point, like a stationary grinder. TTS is a unique and powerful coordinate system similar to tool. However, it's great for deburring or grinding when the work surface of the tool is a cylinder. Instead of rotating the whole end effector, the TTS coordinate system automatically rotates based on the direction of motion. So in this example, you could apply a controlled force in TTS Y direction and just have the robot follow the perimeter of the part without changing orientation. Altogether, RSI and force torque add some really powerful capabilities to KUKA industrial robots. This final video shows insertion of a bobbin into a valve body. With RSI and force control, this assembly is reliable, even though the fit tolerance of the parts only has a few microns of clearance. With sensor feedback in the control loop, we can achieve performance way beyond the positioning accuracy of any industrial robot. Thank you for joining me today. I appreciate your time, and I hope you enjoyed learning a little bit more about KUKA, force torque, and RSI.
I'm open for questions. And it's possible that if we need to, we could do some more detail or some live view of the editor, if anybody's interested in that.
I can go over a couple of these questions if you would like to answer two of these. There's two in here right now.
Sure.
Are the control PID blocks used to compute torque commands for the robot motors?
They are not directly used for that. The PID in the RSI context is much more general and can be applied to whatever control laws you're building. So the KUKA system has various different processing layers. And so there's a top level motion planning layer. And then RSI works on a little lower layer at 4 milliseconds. So then when corrections are sent off to the servo drives, they actually have PID loops in the control hardware that the PID loop on the control hardware it operates at a really, really high data rate, like down in the microsecond range. So the 4 millisecond PID would be if you have something that you're trying to set up control for at that 4 millisecond range. Maybe you have some sensor input that has a higher interval, and you need to do the PID control on that.
Alrighty. So the next question, is it possible to implement impedance control scheme with this interface?
Impedance control. Yes, it is possible to do something like that. You have everything there that you need. You have motor current and gear torque feedback. So the main thing, if you were doing impedance control, is that you need to come up with the control laws and modeling to understand the relationship between the torque and position, because adjustments in RSI are always position based. So either sending axis adjustments or Cartesian adjustments, you're always doing either a angle or position offset, and those are related to the amount of torque that you would generate when you put it in the 4 millisecond control loop. You can still implement essentially like an impedance control.
All right, another question. Are there another sensors we can use similar to this application?
Are there other sensors that we can use? I'm not sure exactly what context that you're asking that in. So I guess I can just do a quick summary. In the context of the force control, we support any sensor, any 6-degree freedom force sensor. So if you have ATIs, like I said, we have direct drivers to read the ATI and do control with those, with a lot of the extra data and features that they offer. But if you have a sensor that just, say, is Ethernet IP or some other field bus data, you can also set that up and use it in force control. or even an analog. You could have a completely analog force sensor and read that in through some A to D cards, and you could use that. So that's in the force torque area. But otherwise, like I said before, any sensor that you can get data on our field bus, you can integrate in RSI. So if you have, say, a laser distance sensor, or some sort of a color sensor that inputs color onto the field bus, or vision. We've shown some examples of vision adjustment there. If you had something that could detect audio volume and get that on the field bus, you could use audio. So really, anything that you can get in on our field bus switches, maybe I should explain that more. Field bus systems that are supported by KUKA are things like Ethernet IP, Profinet, EtherCAT, Profibus, DeviceNet, CC-Link. These are all different field buses, and there's several others as well.
Okay, the next one. Can you use Ethernet control to send path information and force feedback from an ATI sensor to provide additional adjustments?
Yes. As I mentioned, we have direct drivers for the ATI sensors. So their main sensor types are the net FT sensors, which do kind of a generic UDP packet. So we have a direct driver to read the net FT data. They also have a new class of sensors that support EtherCAT, and EtherCAT is our native field bus in KUKA, so we integrate very directly with those.
Okay, next one. Is it possible to combine two force sensors from two different controller in one interface? We have two robot master slave using RoboTeam.
All right, that could be more challenging. The force torque system is really built on the concept of using a single force sensor directly on the end of arm. However, the force control blocks and the RSI blocks are all very generic. So you could build a custom RSI program to read data from multiple sensors. It's just that when it comes to evaluating the active TCP, I think there might be some breakdowns in the paradigm of how it's intended to work. But you could still, like I said, use the RSI blocks directly to do some other supplemental processing of data from multiple sensors.
Okay, this question says, I have an analog ATI sensor. You integrate directly with that, or is there a different preferred interface?
Yes, we can use analog ATI sensors, and actually that's the type of sensor that we started out with supporting when force torque first came out in the 2005 period. I believe we still support even the input of the calibration file from ATI.
Can you clarify how you connect sensors to the KUKA field bus?
Okay. We have a software called Work Visual, which you could think of as like the Visual Studio for KUKA robots. Part of the setup of a KUKA robot uses Work Visual to set up and define your field bus. So essentially that is a process of, say, bringing in the catalog file of your sensor, say like an EDS file, for example, and then adding that onto the field bus as a device, and then mapping the the data from that device onto our input-output system. So it's all very drag and drop. We actually have probably some webinars available online that show I/O mapping and setup in Work Visual.
Is there a C++ SDK for RSI if we want algorithms to lie outside the RSI visual framework blocks?
No, the external interface would be basically through the Ethernet block. So that passes data in and out by XML packets on UDP. So that would be the API hook to do processing outside of the robot controller. We could supply some C++ libraries that would facilitate that communication link. We could also refer you to the ROS industrial driver that supports RSI, which has that sort of C++ communication link already built.
For TTS, is the force measured the force at the sensor, or is it the force applied at the tool?
That's one of the nice things about the force torque system, because it does all the math for you in order to give you the sensor, the force values at the TCP or at the working point, which is always referred to by the TCP. So you can get the raw data values from the sensor as well, but typically you're going to work with the working point at the TCP. And that's true for all of the different coordinate systems. TTS, tool, base is kind of a little bit different way of thinking of it, because when you use base, you're still reading the force at the TCP point. It's just that all the directions are base directions, so they don't rotate with the TCP.
Is RSI an additional option that we have to purchase, or is it included by default for all supported controllers?
RSI is an add-on option. It's a tech package that is an additional purchase. If you use force control, if you get the FTC, it has RSI bundled into it, so you don't have to purchase those separately.
Is RSI an option that we have to purchase, or is it default for all controllers? Okay, so
yes, RSI is an additional purchase option.
Can we do FT control without using RSI?
Sure. If you have a simple force sensor, say 1 degree of freedom or something, and you get it on the field bus, you could do that. The value add for the FTC package is that it does all the math internally to get the values at the TCP. So those are not simple calculations, especially when you consider the gravity compensation for the end effector and all that.
With force control for our particular application, we hold a part with the robot and take it to a grinder. Is there a way to get the force as the grind moves across the part?
Yes. In that case, you probably would be wanting to do the base coordinate for the force control. So that's going to give you the forces aligned in that base direction. So it doesn't really matter since the orientation of the coordinate system for the base is fixed. It doesn't really matter what your contact point is. It'll still always calculate the forces in the right directions. And we've had plenty of applications doing just what you're saying.
All right, there are no more questions at this point that we see. Thank you very much on behalf of KUKA Robotics for joining our webinar.
Industrial Intelligence.